In this lecture, let us discuss FIR filters of type 2. Okay, so we are discussing linear phase filters, and as I said, a linear phase is an extremely important criterion in any system, and we said that only FIR filters can realize exact linear phase, and no other way you can realize linear phase. Okay, even if you use IR filters, you can't realize a linear phase, and even if you use some other analog filters, it's very difficult to realize linear phase. But with the FIR filters, it's very easy to realize a linear phase. Okay, and we also stated that the condition for linear phase, right? The condition for linear phase is that the impulse response is either symmetric or it can be antisymmetric, and this is the first condition. Therefore, symmetric means h of n is equal to h of capital N minus n. This is for symmetric, and h of n is equal to minus of h of capital N minus small n. This is for antisymmetric. And now, since we are discussing FIR filters, finite impulse response filters, the impulse response has only finite number of elements. Let's say h of 0, h of 1, h of 2 and up to h of capital N. So these are finite. And so how many samples do I have here? Capital N plus 1 number of samples. So this n plus 1 is called length of the filter. Length of the filter, and this n plus 1 can be either odd or even. So I have two more classifications now. Previously I have two classification, symmetric or antisymmetric. Then if you combine these two, then we had four types, and from this capital N is called order of the filter. Order of the filter. So now, depending on even and odd length, and depending on symmetry and antisymmetry, we stated that we have four types of filters, and out of these four types we discussed type 1. Okay, now let us recall this type 1 quickly. So type 1 was symmetric, and the length is odd. Okay, don't confuse length of the filter and order of the filter, and order is even. So this is the condition for type 1 filter. And then under this condition we showed that the transfer function h of z is equal to z to the minus capital N times h of z inverse. So this is for type 1 that we already showed in the last lecture. Okay, now what is this? This transfer function or this relation shows that as in all pass filter. Okay, this is a condition for all pass filter that we already discussed. Therefore, if z naught is 0, then 1 by z naught is also a 0. Okay, so this is a condition. That means what? If you make h of z naught, substitute z naught in the polynomial h of z, then you will get 0. Similarly, if you substitute h of 1 over z naught, then also you will get 0. Okay, if z naught is 0, then 1 by z is also a 0. It applies to all the types, type 1, type 2, type 3, type 4. Okay, therefore the zeros occur in reciprocal pairs. Okay, so let me call this is relation 1, and this relation 1 is true for type 1, type 2, type 3 and type 4 filters. Okay, and we also showed in the last lecture that h of 1 is the same as h of 1, and h of minus 1 is also the same as h of minus 1. So therefore, there are no restrictions. In other words, type 1 filter does not have a 0 on the unit circle unless you introduce it intentionally. Okay, but the type 1 filter does not have a 0. Now let us discuss type 2 filter. Okay, and in type 2 the order is odd, and therefore no, let me discuss formally. In type 2 again symmetric, and the length is even now. Okay, the length is odd in the previous case, now the length is even, that is n plus 1 is an even number. And what about n? N is the odd number, that's it. So this is your type 2 filter. Symmetric means what is the condition? H of n is equal to H of capital N minus small n. Now let us take an example and then we will derive the generalized formula. Straight away if I go to the generalized formula, then we may not understand how that formula comes and what way and it has come, so it's very difficult to understand. So let's take an example, and from that example we will write down the general expression for a given order and given length. So it is easy to approach this type 1, type 2, type 3 and type 4 filters through example. Now let me take n is equal to, see this n is an odd number, so let me choose 7. So therefore I have h of 0, h of 1, h of 2 and so on up to h of 7. So instead of writing h of 0 every time, let me write h suffix 0, h suffix 1, h suffix 2. It's very easy to write, that's it, nothing else. Okay, so I have this is 0th point, h0, h1, h2, h3, h4, h5, h6, h7. And what is the condition says? The condition says h of n is equal to h of capital N minus small n, where n is the 7 here. Therefore h of n is equal to h of 7 minus n. Now substitute n is equal to 0, h of 0 is equal to h of 6, isn't it? Am I correct? No, h of 7, because n is 0, no? 7. Substitute n is equal to 1, h of 1 is equal to h of 6. Substitute n is equal to 2, h of 2 is equal to 7 minus 2, 5. H of 3 is equal to 7 minus 3, 4. Okay, so all are paired here, all of them have mates. Okay, so all of them have pairs. So symmetry is around n by 2, where n is 7, n by 2 is 3.5. So symmetry is at this point, this is n by 2, that is 3.5. Okay, so that means what? Your h0 is paired with the h7. Okay, 0 and 7, 1 and 6, then 2 and 5, and 3 and 4. So all of them have pairs. Okay, but at n by 2 the sample does not exist. Okay, so because it is not an integer, right? 3.5 is not an integer, so sample does not exist at that point. So the midpoint is around 3.5, where a sample does not exist, and this gives some special properties. Let's see what that properties are. So h0 is equal to h7, h1 is equal to h6, h2 is equal to h5, then h3 is equal to h4. So now let me write down the transfer function. We know the formula to find out the transfer function. How will we find? By taking the z transform. What is the formula for z transform? Summation of h of n z to the minus n, where n goes from minus infinity to plus infinity. Substitute, you'll get it. So h of z is equal to h0 times z to the 0 plus h1 z to the minus 1, h2 z to the minus 2 plus h3 z to the minus 3 plus h4 z to the minus 4, but h4 is same as h3, so here I will write down h3, okay, plus h5 z to the minus 5 plus h6 z to the minus 6 plus h7 z to the minus 7. Okay, now as I said, h7 is the same as h0, so let me put h0 here, and then h6 is the same as h1, let me put h1 here, and then h5 is the same as h2, and then h4 is same as h3. Now you can rearrange this, then you will get h0 commonly take outside, z0, let me write down z0 instead of writing z0, 1 plus z to the minus 7 plus h1 z inverse plus z to the minus 6 plus h2 z to the minus 2 plus z to the minus 5 plus h3 z to the minus 3 plus z to the minus 4. Now what I can take out now is z to the minus 7 by 2. Okay, so let me take z to the minus 7 by 2 commonly outside, that means I am taking 3.5 outside. So here h0 z to the plus 7 by 2 times z to the minus 7 by 2 plus h1, here z to the plus 5 by 2 plus z to the minus 5 by 2, okay, plus h2 times z to the 3 by 2 plus z to the minus 3 by 2. Okay, plus h3 z to the half plus z to the minus half. Okay, now in order to find the frequency response, we have to substitute z equal to e to the j omega in the above expression. So h of same procedure, h of e to the j omega is equal to e to the minus 7 by 2 minus j 7 by 2 omega e to the minus j 7 by 2 omega within a bracket h0 plus e to the j times 7 by 2 omega plus e to the minus j 7 by 2 omega plus h1 e to the j 5 by 2 omega plus e to the minus j 5 by 2 omega plus h2 e to the plus j 3 by 2 omega plus e to the plus j minus j 3 by 2 omega plus h3 times e to the j omega by 2 plus minus e to the minus j omega by 2. Now again you can use Euler's identity, and this can be written as cos of 7 by 2 omega. So e to the minus j 7 by 2 omega multiplied by 2h0 cos of 7 by 2 omega plus 2h1 cos of 5 by 2 omega plus 2h2 cos of 3 by 2 omega 2h3 cos of omega by 2. Now this is called a pseudo magnitude, that as I said h tilde, we gave some special symbol for this, h tilde of omega. So on the left hand side h of e to the j omega, therefore h of e to the j omega is equal to e to the minus j 7 by 2 omega times h tilde of omega. Now this guy will give you the linear phase. What is that linear phase? Minus 7 by 2 omega, and this offers phase shift of, let's say that phase is called beta, and this is in terms of 0, pi, 2 pi, 3 pi, some discrete jumps. Okay, so this is your phase. Now what is the group delay? Group delay, as I said, it is denoted by tau suffix g of omega, and this g denotes group, and this tau is denotes delay, and this is equal to negative gradient. That means differentiation of your phi with respect to omega. So therefore minus 3.5, sorry, plus 3.5 plus this guy, anyway you can't differentiate discrete points. So the linear phase is obtained as 3.5. Sorry, the delay is obtained, the delay is 3.5 samples. Okay, this 3.5 indicates 3.5 seconds or microseconds or milliseconds, doesn't matter. Okay, so and moreover the thing is, the 3.5 is not an integer. Okay, it is not an integer number. It is 3 samples plus another half sample. So this creates problem in realization, because you cannot realize a half sample. You know, in digital signal processing with uniform sampling, our time index is an integer. Okay, so if you recall, the sampling index an integer. Okay, it's not a rational, it's not a decimal number. Therefore this 3.5 produce a delay of 3.5 samples, and in general if you take h of n is equal to h of capital N minus small n, and n plus 1 is even, then n is odd. Therefore this n by 2 will become a 3.5. Okay, so that's one thing we need to note down in type 2 filter. Okay, so the summary is h of n is equal to h of n minus small n, symmetry, and n plus 1, that is order, length is even. This implies order is odd. Therefore h of e to the j omega in general, how can I write it? If you look at the expression, this, if you look at closely, then e to the minus j 7 by 2 omega, this 7 by 2 omega, that means in general I can write e to the minus j, instead of writing 7 by 2 I can write n by 2. What is n here? We took n is equal to 7. So in the example problem we consider, see, n is equal to 7. So instead of writing 7 by 2, let me write n by 2 times omega. Therefore this part becomes e to the minus j n by 2 omega, and then this whole terms can be written as follows. You put 2 commonly outside, summation of, you have impulse response plus some cos omega term. So I can write h of n plus 1 by 2 minus n cos of n minus 1 by 2 times omega. Okay, where n goes from n is equal to 1 to n plus 1 by 2. Okay, you can substitute values, and then finally you will end up this expression. Okay, now it is also clear that the same relation holds here also. Okay, what is that relation? h of z that we did in the type 1 filter is also holds in type 2 filter also. Z to the minus n h of z inverse. Substitute h of 1, the left hand side h of 1. What about the right hand side? Right hand side is 1 to the minus n. Again that doesn't matter, it's going to be 1. Then h of 1. Therefore h of 1 is equal to h of 1, no problem. Now substitute z is equal to minus 1, then the problem comes. H of minus 1 in the left hand side, the right hand side minus 1 whole to the minus n, h of minus 1. Now what is this? This is an n is an odd number in type 2 filter. So minus 1 whole power odd number, it is going to be minus 1. So this is minus h of minus 1. Now what does this mean? Now how can I relate h of minus 1 is equal to minus of h of minus 1? Okay, so this condition will be satisfied only if h of minus 1 is equal to 0. So that it means that h of z, if it is to be 0 at z equal to minus 1, then it must have a factor of 1 minus z inverse multiplied by some function polynomial h1 of z. Because I have a factor like this, because of that only it becomes 0. See, when h of minus 1 is equal to 0 means what? This is my, let me write my h of z equal to 1 minus z inverse times some polynomial h1 of z. Now you substitute z equal to 1, z equal to 1 in this, then it becomes 0, right? I'm sorry, 1 plus z inverse. Okay, so this relation implies h of minus 1 is equal to 0. So if you substitute minus 1, then this becomes 0, 0 times the polynomial 0, therefore h of minus 1 is equal to 0. Similarly, that's it, yeah. Therefore, in general, you can write h of z is equal to 1 plus z inverse times h1 of z. In other words, with the type 2, is it possible to get a high pass filter? High pass filter can we get in type 2 filters? No. Why? Because in high pass filter we need no magnitude 1 at z is equal to minus 1. Z is equal to minus 1 means what? Omega is equal to pi. But at omega equal to pi, your magnitude is 0. Okay, let's say this is my high pass filter like this, some cutoff frequency omega c. At z equal to minus 1, I need the maximum magnitude in the high pass filter. But in type 2 filter, at z equal to minus 1, the function becomes 0. Therefore, I cannot realize a high pass filter using type 2 FIR filter. Okay, so high pass filter is not possible in type 2 FIR filter. But in type 1 filter, you can realize all types of filters. You can realize low pass, high pass, band stop, all filters you can realize. Okay, so with the type 1, it was not a problem. H of 1 is equal to h of 1 and h of minus 1 is equal to h of minus 1. But here h of minus 1 is identically equal to 0 because n is odd. Therefore, type 2 filter has the limitation that it cannot be used for design of high pass filter. This restriction is not there in type 1 filter. Okay, so that's all about type 2 filters. So the important point is h of 1 is equal to h of 1 and h of minus 1 is equal to minus h of minus 1. So this implies h of minus 1 is equal to 0. Okay, the general relation is h of z is equal to z to the minus n times h of z inverse. Okay, so this means h of z must have a 0 at z equal to minus 1. In other words, I must have a factor of 1 plus z inverse times, let's say, some polynomial h1 of z. So where is the location of this 0? It is here. Okay, this is z equal to 1. So I must have a 0 at minus 1. I'm sorry, z equal to minus 1. And the consequence of this is that a high pass filter is not possible because high pass filter requires a unit t magnitude at z equal to minus 1. See, our range of vision is 0 to pi. In the omega domain, omega is equal to pi is the same as z is equal to minus 1. But at z at z equal to minus 1 or at omega is equal to pi, I should have the magnitude of 1 for high pass filter. But unfortunately in type 2 filter at omega is equal to pi it becomes 0, or at z equal to minus 1 it is going to be 0. So I cannot realize a high pass filter using type 2 filter. Also I cannot realize band stop filter using type 2 filter. Why? The band pass filter has the characteristics like this, BSF. Okay, so again at pi or minus 1, z is equal to minus 1, the magnitude is 0, but I need, for band stop filter I need non-zero value, but in type 2 filter the magnitude is 0, therefore I cannot realize band stop filter also using type 2 filters. So band stop filter and high pass filter, these two filters cannot be realized using type 2 filters, type 2 FIR filter. Okay, so band stop filter and high pass filter are not possible in type 2 filter. Okay, see, band stop filter also requires unity magnitude at omega equal to 0. Okay, as well as this is omega is equal to 0 at I need a unity magnitude, at omega is equal to pi I need unity magnitude. Therefore band stop filter is not possible through this type 2 filters. Okay, so let me stop here. In the next lecture we will continue this topic. Okay, so we will discuss type 3 filter in the next lecture. Thank you very much.